Hello everyone and welcome to another fun adventure with statistics. Today I'm going to go over the worksheet for Chapter 6 probability models, and I'm going to detail the first 4 examples in this video, and then I'm going to try to space it up a little bit better than my last videos for time considerations and ease of upload. So I'm just going to go through the first 4 today. So I'm going to show you how to do this on Minitab. There are other ways to do this, including on the calculator if you wish. But let's go ahead and see what Minitab can do. All right, so first thing I'm going to do is I'm going to read the problem. In a recent survey, 80% of the community favored building a police substation in their neighborhood. If 15 citizens are chosen, what is the mean number favoring the substation? So remember, the mean for a binomial is simply the sample size times the probability of success. So our mean would be 15 times 0.8, which if you look in the solutions is 12. Woohoo! And then the standard deviation is a little bit more complicated. I have to do the square root of 15 times 0.8 times 0.2. So one of the quick and dandy ways you can get around this is you can, I'm just going to write QRT for square root. And since I already did P times N in the first part, I can do 12 times 0.2, which is Q, which will be, I'm doing the inside part first, which will be the square root of 2.4 now, because that's what you get when you multiply 12 by 0.2. And then if you take the square root, you get 1.55. So it tells you that roughly the spread of the distribution is about 1.55 with a mean of 12. Okay, let's look at calculating some probabilities. So according to the government data, the probability that a woman between the ages of 25 and 29 was never married is about 40%. In a random survey of 10 women in this age group, what is the probability that 2 or fewer are never married? So this is a binomial because there's a certain number of successes and a certain number of trials, and we have a defined probability for success. And that's 40%, so that's my P, and there's my sample size N, or my number of trials, and I'm going to go ahead and calculate this probability. So there's a couple different ways you could do this. I'm going to use the graph option because I like the fact that it gives you a plot of what you're looking at. So I'm going to be using the probability distribution plot, and I'll go to probability view and hit OK. And I'm no longer using a normal model, I'm using a binomial, which will be near the top. There he is. And I have to give the number of trials, which is the number of people I'm sampling, which is a 10. My event probability, and this is my success probability, so 0.4. Or maybe 0.6 if you don't want to get married. Ha 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 ha. Okay, fine. And then shaded area. This is where we need to pay attention to which direction we're heading. And since I want less than or equal to 2, I'm going to be putting in an x value and going to the left of that x value because I'm doing less than or equal to 2 and putting the 2 in there and hitting OK. And there we are. And that tells us that our probability, sorry about that, is going to be 0.1673. Now what I don't like about this is it's a little unclear if this is a less than or equal to or a less than, because that does make a difference with the binomial, sorry. Remember, your chances are, you have 10 women, so how many successes could you have? You could have 1, you could have 0, you could have 2, you could have 4, you could have 7, you could have 6. You have to have some countable number. So being less than 2 is looking at the probabilities that you were 0 or 1. Being less than or equal to 2 would be the probability that you are 0, 1, or 2. So it's important for us to note that. And that's the only thing I don't really like about the distribution plot version of this. So let me show you another way you can do this. If you go to calculate and then probability distribution, and then notice there's the binomial, I like this way a little bit better. I'm doing a cumulative probability, not a single value, so I want this radial dot chosen. If I do just a single probability like I'm going to do in B, I would choose probability because it's a single value. So I need to give it the number of trials, which is 10, the event probability, 0.4. And then if you have like lots of things you want to check at the same time, you can use an input column for this. I'm going to use a constant because I'm just doing a single value. And if you want, you can store it somewhere in your data if you're going to use it later for something. I am not. And the value I'm interested in is 2. And now if I hit OK, ta-da! Notice this gives you more accuracy too, more decimal places, and it tells you it's a less than or equal to. Not just a less than, not an equal to, but a less than or equal to. It's a little bit more specific than the graph. So this also teaches you that the graph is a less than or equal to, if you were wondering. Okay. So next I want to do exactly 3. Well, to do exactly 3 in the, probability distribution plot is not really possible. So, oh no, let's hit cancel. But I can do that with the calculate menu. So we're going to calculate probability distribution binomial. I'm still using the same setup, so keeping it 10 and 4, but now I'm going to switch the radial button to probability because I'm looking for a single unit probability, and that's where it's exactly equal to 3. So I'm going to put in 3 and hit OK. So that probability is 0.21 for a bunch of 9s and a 1. That's about where we're at. Okay, more than 5 of them. So I accidentally forgot to delete this, but if you're doing it with more than 5, remember there's 10 women I'm asking, so being more than 5 would be, like 6, 7, 8, 9, 10. So I start at 6 and count accumulating after that because this is we're using equal to, remember? So I don't want to include 5, but I want to include the things that are larger than it, so it starts at 6 because you can't be 5.5 people, so it's not 5.5, it's not 5.1, it's 6. So let's do a graph for this one. And this is an advantage the graph can do since this is an area to the right. Using the cumulative distribution function, it will only do area to the left, so I'm going to use the right version using probability view because it will do the right, unlike the other. All right, these are staying the same, and I want to do area to the right, so I want a right tail, and I'm going to start at 6 instead of 5. We'll hit OK, and there is our graph. So 0.1662. Okay, now let's do between 5 and 6. Now, this is inclusive, so I can do 5 to 7 and not have to use 6 and just 6 because, there's more than just 6 in here. It's 5, 6, and 7. So let's do stat. Oh, I'm going to do graph because this also does the in-between value a little bit better. So probability view, shaded area, middle, and I want my lower to be a 5 and my upper to be a 6. Oh, not 6, sorry, 7. Let's hit OK. The other thing to recognize is that since it's coloring in this 7 bar and this 5 bar, 5 and 7 are included in this probability that I'm calculating. That's another way you can recognize that it's doing this correctly. Okay, now let's look at a new situation. So the probability that a house in an urban area will be burglarized is about 3%. If 25 houses are randomly selected, what's the probability that none of those houses have been burglarized? So I'm looking at a single probability value again. So calculate probability distribution binomial. Here my number of trials is 25 because there are 25 houses, and I'm looking at 3% as, success. I know it seems weird to consider success being burglarized. You might want to probably do the opposite. I don't know. It's an interesting thought. But we want nobody to be burglarized. We have lofty goals of happiness with our probability distribution. We'll hit OK. And we get this lovely detailed number, which I'm going to be lazy and just copy and paste. Look at that. So much faster. If you did this using probability view, you would get a rounded value, which I kind of don't like. Okay. 65% of men consider themselves knowledgeable football fans. Woohoo! If 12 men are randomly selected, find the probability that exactly half of them will consider themselves knowledgeable football fans. So here we're looking at x being 6 because that is half of 12. And we'll go to stat. Probability distribution plot, probability view. I'm going to show you how to do the probability view version of this, which is super weird. My probability that I'm successful is that 65% that actually know some football, and there are 12 people in my sample, and now I'm going to do shaded area, and here's how you get exactly 6. This is very strange. So you might be thinking, oh, tails and things like that, but that'll shed area above and that'll share area below. And I don't want to do like above and below. I want to do a single value. So I want the numbers between 6 and 6, and this is super weird. Here we go. That's how you get exactly 6. Another reason I like the other one a little bit better, but it's just because it's a little strange looking. Sorry. Because you're less than or equal to 6, and you're sorry, greater than or equal to 6, less than or equal to 6. The only thing in there is 6. Fun times. Okay, well, that about wraps it up for today. I hope you enjoyed this video. Oh, why did I get all high at the end? That was weird. See you later.